In this section, we want to introduce two new functions, exponential and logarithmic functions. We'll start off with the exponential function, which are functions of the form y equals a to the x, where a is some constant greater than 0 and not equal to 1. We have the graph of two different exponential functions below. The first is the graph of y equals 2 to the x power, as an example of one exponential function. This is a case where our value for a, which in this case is equal to 2, is greater than 1. We can see that this is a one-to-one function because it would pass the horizontal line test. It has a domain from negative infinity to infinity, and it has a range from 0 with an open bracket at 0 to infinity, meaning our function will continue approaching but never cross that line y equals 0. What that means is that this function actually has a horizontal asymptote defined by y equals 0. So as we approach to the right, our function is going, or as x approaches positive infinity, our function is going to continue increasing. But as we approach negative infinity, or as x approaches negative infinity, our function value will approach closer and closer to 0. And our function will always hit a few key points, which we can use to sort of sketch out our graphs. In this case, our function is hitting -1, 1/2, 0, 1, and 1, 2. To generalize that, we could say that our exponential function, in the case where a is greater than 1, will always hit the points 0, 1, -1, 1 over whatever our value for a is, and then +1, a. We can also say that our function is increasing for all real numbers, or on negative infinity to positive infinity. On the right, what we have is the graph of y equals 1/2 raised to the x power. So now we're dealing with a case where a is equal to 1/2 is less than 1. In that case, we can see what changes is that our function is now decreasing on negative infinity to infinity. So whenever our exponential function has this value a, which we refer to as its base, somewhere between 0 and 1, so we can be a little bit more specific here, then our function is going to be decreasing. We still have this same horizontal asymptote, but the end behavior has shifted. Now as x approaches negative infinity, our function values are headed off to positive infinity, and as our x values approach positive infinity, our function value is approaching 0. So that same behavior, just flipped. And our function will always hit the points -1, a, 0, 1, and 1, 1 over a. In this case, we can see that as the point 0, 1, -1, 2, and 1, 1/2. So depending on our value for a, we get a few characteristics of our exponential function that change. It's also going to be important, as we're dealing with exponential functions, to keep in mind the difference between an exponential function, which is something of the form y equals a to the x, versus a power function, which is something of the form y equals x to the a, or x to the n power, as we've typically written it in the past. The difference is where the variable and the constant are positioned. With exponential functions, we have a constant raised to some variable. With a power function, we have a variable raised to some constant. Below, we have a couple of example functions graphed. in this case y equals 2 to the x and y equals x squared, so we can see the difference in the behavior. Of course, our x squared function is going to follow that parabola shape. Our exponential function and our power function are going to intersect at a few key points here. And we're going to see what will happen during those different windows is it will change back and forth which function is taking on the larger function values. If we consider what's happening between that first and second point of intersection, what we have is our exponential function taking on larger function values than our power function. In that second range, that gets flipped around, and our power function is actually taking on larger values than our exponential function. But then after this third point of intersection, that flips around again and continues for the remainder of these functions as x approaches positive infinity. So over time, or for large enough values of x, in this case we're only around x equals 4, exponential functions are going to take on significantly larger function values than power functions. If we look at the graph on the right, we can see that in even better perspective. Here we have y equals 2 to the x power again, and y equals x squared, just graphed on a different viewing window. What we can see is that this exponential function is increasing dramatically faster than that power function. And this is what we refer to as exponential growth, an idea that you've most definitely heard of in different scenarios. But exponential growth is just this idea of very, very rapid growth, in this case significantly faster than what we would see with a power function or a polynomial function.